Hello and welcome to a continuation of the previous two videos on Basic Mathematics by Serge, where we were in... We were solving exercises 1 through 21 of sections 1 and 2 with the integers and rules of addition. I did not see that on the back. We had 2 more questions, so we'll complete those questions and then move on. So then we have problem 22. Prove the cancellation law for addition. And I taped a sheet of paper onto the glass surface just to give it a little more friction so that it doesn't slide all over the place while I'm writing. Though it still does, so a little, but at least helps. You know, properties of continual improvement, Kaizen. So prove the cancellation law for addition. Cancellation law, as stated, is, wait for the book, if A plus B equals A plus C, then B equals C. So effectively, if we have A on both sides, we can get rid of A, and, well, whatever will remain will still remain. So, sort of like cancellation law. Okay, so that's, I believe, quite easy. All we have to do is subtract A from both sides. So A minus A plus B equals A minus A plus C. 0 plus B equals 0 plus C. And then by N1, B equals C. And then what we could do, I think, is, well, I mean, I think we proved it right there. Is there a possibility that we can try to prove this in another way, like proof by contradiction? We could try that. So let's try proof by contradiction. So let's assume A plus B does not equal A plus C. Okay, well, yeah, we can say that. Because then we can do the exact same thing as we did above, where we subtract A from both sides. And we did this by subtracting A from both sides. Then we get 0 plus B does not equal 0 plus C. And then we use by N1, B does not equal C. But we've already assumed that B does equal C. Here we have a contradiction. Therefore, our original assumption. Must be true. If B equals C, of course. So we proved it in two different ways. Overkill, I think. Then we have question 23. Prove if A plus B equals A, then B equals 0. So effectively, if we can remove B from this equation, A equals A. So let's try to do it with both methods, just as we did with 22. Okay? So then, let's simply subtract A. No, not. Yes, A from both sides. Also, I think I meant to say B. If we move B, A equals A. Or maybe I said it right. Washing machine is distracting me. But one must do wash. Okay, so then A minus A plus B equals A minus A. That simply equals 0 plus B equals 0. And then by N1, we have B equals 0. N1, which is 0 plus A equals 0. Not 0. A. See, just that paper taped to the helping a lot. I was able to erase it without it just going everywhere. Little improvements. Okay, so then, well, B equals 0, B equals 0. If this is true, then that is true. We got there. We got there. Well, we got to here by using legal methods. So we subtracted A from both sides, which does not affect our equal sign. We use N1, that does not affect our equal sign. It is assumed to be true. And, well, we get B equals 0. So B equals 0, B equals 0. Everything's true. So effectively, checks off. Alright, now let's try by contradiction. We assume A plus B does not equal A. Then B equals 0. Okay. Effectively, we're going to do the same thing. A minus A plus B does not equal A minus A. And we get 0 plus B does not equal 0. And then we get B does not equal 0. And this was by N1, by addition, subtraction, and this was by subtracting A on both sides. So we get B equals 0, then B does not equal 0. Well, B does not equal 0, then B equals 0. We have, of course, now a contradiction. Okay. A plus B must be false. Therefore, A plus B equals A. B equals 0 must be true. Must be true. Okay, put that aside. That completes question 22 and 23. And now we're moving on to section 3, rules for multiplication. So, we can multiply integers, and the product of two integers is again an integer. We shall list the rules which apply to multiplication and to its relations with addition. We again have the rules of commutativity and associativity, where we have AB equals BA, and AB in parentheses times C is equal to A times BC in parentheses. We emphasize that these apply whether A, B, C are negative, positive, or 0. Multiplication is also denoted by a dot. For instance, 3.7 equals 21. So this is in contrast to what we're sort of shown in school, where we're sort of shown like 2 times 4. In reality, we should be writing 2, not 4. For any integer a, the rules of multiplication by 1 and 0 are this rule number 6, where 1 of a equals a, and 0 of a equals 0. So whether a is positive, negative, or 0, multiplying it by 1 does not change it, and multiplying it by 0 means it becomes 0. For example, we have 2a, 3b, or 2a in parentheses times 3b in parentheses equals, we shuffled around using the rules of associativity, 2 times a times 3b in parentheses, and it also could equal 2 times 3a in parentheses times b, and it could also equal 2 times 3 in parentheses times ab, and it could also equal 6 times ab. So what it doesn't say right here is that multiplication is also denotated by a dot. It's also denotated by just I guess a proximity. So AB is A times B. So what we have here is, well, this is a horrible example because 24 doesn't mean anything. Well, that means like the number 24. A little difficult. But say we have A, B is equal to A times B, which is equal to A dot B in this circumstance. Now, once we hit linear algebra, these are going to mean different things. And also vector algebra, or, well, math with vectors, because then that's going to mean a dot product. It may mean a dot product in future, and this may mean the cross product between two matrices or whatnot. So for the moment, we will be using this and this. We will be excluding that. In this example, we have done something which is frequently useful. Namely, we have moved to one side all the explicit numbers, like 2, 3, and put them on the other side, those numbers denoted by a letter, like A or B. Using commutativity and associativity, we can prove similarly that 5x in parentheses times 7y in parentheses equals 35xy. Or, with more factors, 2a in parentheses times 3b in parentheses times 5x in parentheses equals 30abx. We suggest that you carry out the proof of this equality completely, using associativity and commutativity for multiplication. Finally, we have the rule of distributivity. Distributivity. Namely, A times B plus C in parentheses is equal to AB plus AC. And also on the other side, it works from both directions. we have B plus C in parentheses times A is equal to BA plus CA. These rules will not be proved, but will be used constantly. We shall, however, make some comments on them and prove other rules from them. First, observe that if we just assume distributivity on one side and commutativity, then we can prove distributivity on the other side. Namely, assuming distributivity on the left, we have B plus C times A, B plus C in parentheses times A is equal to A times B plus C in parentheses, which will equal AB plus AC, which is also equal to BA plus CA, which is the proof of distributivity on the right. Observe also that our rule 0A, or 0 times A equals 0, can be proved from the other rules concerning multiplication and the properties of addition. We carry out the proof as an example. We have 0A plus A is equal to 0A plus 1A, which is equal to 0 plus 1 in parentheses times A, which is equal to 1A, which is equal to A. Thus, 0 times A plus A equals A. Adding minus A to both sides, we obtain that 0A plus A minus A equals A minus A equals 0. The left-hand side is simply 0 of A plus A minus A equals 0 of A plus 0 equals 0A, so that we obtain 0A equals 0, as desired. We can also prove, in N7, Rule 7, that minus 1 times A equals minus A. The proof. We have minus A times A plus A equals minus A, minus 1 times A plus 1 plus A equals minus 1 plus 1 in parentheses times A, which is equal to 0 times A, which is equal to 0 as we proved before. By definition, minus 1 of A plus A equals 0, meaning that minus 1 of A equals minus A, as was to be shown. We have Rule 8 and 8, number 8, minus AB in parentheses is equal to minus A in parentheses times B. Now we have proof. We must show that minus A in parentheses times B is the negative of AB. This amounts to showing that AB plus minus A in parentheses times B equals 0. But we have, by distributivity, AB plus minus A in parentheses times B equal to A plus minus A in parentheses times B equals 0 times B equals 0. Thus proving what we wanted. Similarly, we leave to the reader the proof that N9, that minus AB is equal to A times minus B in parentheses. So effectively, we have this negative outside of the numbers, and we can put that negative onto either one of the components. For example, we have minus 3A in parentheses equals minus 3 times minus 3 in parentheses times A is equal to 3 times minus A in parentheses. Also, we have 4 times A minus 5B, and we can distribute this 4 into this A minus 5B in parentheses to get 4A minus 20B. We also have we have minus 3 times 5a minus 7b in parentheses, and we could distribute in this minus 3 to 5a and 7b to get minus 15a plus 21b. In each of the above cases, you should indicate specifically each one of the rules we have used to derive the desired equality. Again, we emphasize that you should be especially careful when working with negative numbers and repeated minus signs. This is one of the most frequent sources of error when we work with multiplication and addition. For example, we have minus 2a in parentheses times 3b in parentheses times 4c in parentheses. So we could put all of the explicit numbers on the left-hand side. So we have minus 2 in parentheses times 3 times 4 times abc. And we can multiply all of the explicitly stated numbers to get minus 24, and then multiply that by our remaining letters abc. Similarly, we can have minus 4x in parentheses times 5y in parentheses times minus 3c in parentheses, which can equal, with all of our explicit numbers on the left, we have minus 3 in parentheses times minus 4 in parentheses times 5 times minus 3 in parentheses, followed by x, y, c, all of our letter characters, or letter numbers on the right. This equates to 60x, y, c. Note that the product of two minus signs gives us a plus sign. For example, if we have minus 1 in parentheses times minus 1 in parentheses, we get 1. To see this, all we have to do is apply our rule. With minus ab in parentheses, you could get minus a in parentheses times b, or we could get a times minus b in parentheses. We find that minus 1 in parentheses times minus 1 in parentheses can equal minus 1 times minus 1 in parentheses. Or what we could get is progressing that, we could get minus 1 in parentheses, which these two minuses cancel out, and we get 1. For example, an example. More generally, for any integers a and b we have rule number 10, where minus a times minus b equals ab. The minus signs cancel each other out. We leave the proof as an exercise. From this, we see that a product of two negative numbers is positive, because if a, b are positive, and minus a, minus b are therefore negative, then minus a, minus b is the positive ab. For instance, minus 3 and minus 5 are negative, but minus 3 in parentheses times minus 5 in parentheses equals minus 3 times minus 3 in parentheses to get minus 3 times 5 in parentheses to get 15. 15 with the product of 3 and 5, and then the two minus signs canceling each other out, and we get positive 15. Example. A product of a negative number and a positive number is negative. For instance, minus 4 is negative, 7 is positive, and minus 4 times 7 is equal to minus 4 times 7 in parentheses. This equals minus 28. So that minus 4 times 7 is negative. When we multiply a number with itself several times, it is convenient to use a notation to abbreviate this operation. Thus we write a times a is equal to a squared. A times a is equal to a cubed. And we have a times a times a times a is a to the 4th power. And in general, if n is a positive integer, a sub n is equal to a, however many a's there are of n. We say that a sub n is the nth power of a. Thus, a squared is the 2nd power of a, and a sub 5 is the 5th power of a. If m and n are positive integers, then we have rule 11. A to the power of m plus n is equal to the product of a to the m times a to the n. This simply states that if we take the product of a with itself, m plus n times, then this amounts to taking the product of a with itself m times, and multiplying this with the product of a with itself n times. For example, we have a squared times a cubed is equal to a times a in parentheses times a times a times a in parentheses, which could also equal to a to the power of 2 plus 3, or a times a times a times a times a, or a to the 5th power. For example, we could have 4x to the power of 2, where we have 4 times x times 4 times x. Or we could move our explicit numbers to the left and our non-explicit letter numbers to the right, where we have 4 times x times x. Or, if we multiply them together, we can get 4 times 4 equals 16, and x times x, or x to the 2nd power, or x squared. For example, we could also have 7 times x in parentheses times 2 times x in parentheses times 5 times x in parentheses. We can move all of our explicit numbers to the left and our non-explicit numbers to the right. And so we have 7 times 2 times 5 times x times x times x. Or 7 times 2 times 5 equals 70, and x times x times x equals x to the 3rd power, or x cubed. So we have 70x cubed. We have another rule for powers, namely rule N12, where the product, taking a to the m power and raising it to the n power is equal to the product of it is equal to the raising of a to the product of m times n. This means that if we take the product of a with itself m times, and then take the product of a to the m with itself n times, then we obtain the product of a with itself m times n times. Example, we have a cubed to the 4th power is actually equal to a to the 12th power. Sorry. It's too far zoomed in, the book's too far towards me. I shall adjust. Example, we have a times b raised to the nth power is equal to a to the n times b to the n, because a times b to the n is equal to ab times ab times ab times however many n's remaining. And then we could group by the rules of commutativity. We could move all the a's on the left side and all the b's on the right side, and they're both of n signs. They're both of n quantity, so we can convert those strings of a's and strings of b's to a sub n and b sub n. Example, we have 2 times a cubed raised to the 5th power. What we can do is we can take this 5th power, apply it into our parentheses to 2 and a sub 3. So we have 2 to the 5th power now, and then we have a sub 3 now to the 5th power as well. And now we can take the product of 3 and 5 to get 15. And this is our new power of a. And we can take 2 to the 5th power, which is 32. So we have 32 times a to the 15th. An example. The population of a city is 30,000 in 1930 and doubles every 20 years. What will be the population after 60 years? This is a case of applying powers. After 20 years, the population is 2 times 30,000. After 40 years, the population is 2 to the 2nd power times 30,000. After 60 years, the population is 2 to the 3rd power times 30,000, which is the correct answer. Of course, we can also say that the population will be 2,040,400,000. The following 3 formulas are used constantly. They are so important that they should be thoroughly memorized by reading them out loud and repeating them like a poem to get an oral memory of them. We have a plus b to the 2nd power is equal to a squared plus 2 times ab plus b squared. We then have a minus b to raise to the 2nd power is equal to a squared minus 2ab plus b to the 2nd power, b squared. We also have the product of a plus b in parentheses times a minus b in parentheses, which is simply equal to a squared minus b squared. So, how I like to remember this, or at least with the bottom one, is nice and easy, is that a plus b times a minus b, you can imagine that these cancel each other out. The plus and the minus, they sort of fight against each other, and you don't end up with a middle part. Okay? And if you have a plus with your a plus b squared, you're going to have a plus 2ab. But if you have a minus in your ab, you're going to have a minus 2ab. But beyond that, there is no difference between them all. So, find your own way and memorize these as best you can. I only truly remember, I think, a plus b times a minus b for the most part, but I do know these exist every time I see them. They're like burned in my memory, but I have to redo them. I don't know them by heart, but I know how to get there. Like I'll do it in my head to get here from here. But you know, it's sort of like remembering that 7 times 3 is 21 versus knowing 7 times 3 equals 7 plus 7 plus 7, and 7 plus 7 is 14, plus 7 equals 21. One of them is a lot faster than the other. And so, sort of memorizing it is a good strategy. Proofs. The proofs are carried out by applying repeatedly the rules for multiplication. We have a plus b to the 2nd power is equal to split this up into two pieces, a plus b times a plus b, and then we're going to distribute a out. Are we distributing a out? No, we're distributing a times a plus b, and then b times a plus b. So then we have a times a plus b plus a times b. And then what we have is we have a times a. We're using the rules of distributivity of multiplication. So we have a going into a plus b, which will equal a times a plus a times b. And then over here we'll have b times a plus b in parentheses to get ba plus bb. And then we'll have, with 2 a's, a times a, we can say that's a squared, and we have ab, and then what we can do is we can use the commutativity property of multiplication to swap around ba to be ab, and so we have ab plus ab, that will be 2ab, and then on the last part we have b times b, which we can write as b squared. So then, of course, we have a plus b raised to the second power equals a squared plus 2ab plus b squared. Which proves the first formula. We have a minus b squared equals a minus b times a minus b. Or, in this case, we can distribute the a times a minus b and distribute the minus b times a minus b to be over here. We have a times a minus b, and we have minus b times a minus b in parentheses. So then we have a times a minus a times b minus b times a plus b times b. With these minus signs canceling out, notably, to get b plus b. Well, b times b, negative b, well, minus b equals, well, just b times b. Two minuses or negatives multiplied together equals a positive. And then we have AA, which can be written as a squared minus AB, and we use the rules of commutativity of multiplication to switch this around from BA to AB, and so we have minus AB, which we can sort of add those together to get minus 2AB, since we have two ABs. And then we have our BB, which can be written as B squared, and so we have plus B squared. So A minus B to the second power is equal to A squared minus 2AB plus B squared, which proves the second formula. Finally, we have A plus B, the third formula, A plus B in parentheses times A minus B in parentheses. So then, we have A, we're doing just the distributive property of multiplication. We're going to distribute A to A minus B and then B to A minus B. So, we have A times A minus B in parentheses plus B times A minus B in parentheses. Or, this will equal to A times A minus AB plus B times A minus BB. And we can write our A times A as A squared, and we can use, and then we have minus AB plus AB with using the rules of commutativity, swapping out B and A for A to B. So we have minus AB and plus AB, which would be 0 and taken out. And then we have minus BB, which can be written as B squared. So we have minus B squared. And finally, with A squared and AB, and with minus AB and positive AB canceling each other out, we are finally left with minus B squared. So A plus B in parentheses times A minus B in parentheses is equal to A squared minus B squared, which proves the third formula. So, for example, we have 2 plus 3 times x raised to the second power, which we can distribute this second power to 2 and 3 times x to equal 2 to the second power plus oh yes, one second. Okay, sorry about that. I had to switch my wash over. My chair was eating my pant leg. Okay. Let's get back into this. Where were we? We were here, for example, 2 plus 3x to this square power. That is going to equal, well, if we imagine, we will. Let's grab a sheet of paper here. I hate this flippy. So I use something like this to weight it down. I don't like when the subject of what I'm talking about is on the left-hand side of the book, because it makes it really difficult, because I have this shelf, this drop. So So I can't just lay a piece of paper across. Like I almost need an adjustable stack of some kind, such that I can lay a paper across and write across without it drooping down. Well, to wish, to wish. Okay, so then we have 2 plus 3x squared. We can imagine this is equal to a plus b squared, okay, where a is equal to 2 and b is equal to 3x. And we know that a plus b squared is equal to a squared plus 2ab plus b squared. We know this, and we prove this just back here. A plus b to the second power is a squared plus 2ab plus b squared. And then all we have to do is substitute a's and b's for our 2's and 3x's. Okay, so then a being 2, so we have 2 to the second power plus 2 times 2 in parentheses just to denote. And then we have b, which is 3x plus 3x to the second power. Okay, so is that what we got here? Yes, so that's how we got, very quickly, is how we got from 2 plus 3x to the second power to this first line. That wasn't described, but like we will be using that formula, we're just using this. So effectively, this is what's happening. How it got there. Okay, so then we can just simply perform this operation. I've written it slightly differently. So instead of using dots, I'll use parentheses and adjacencies to denote multiplication. But we have the same thing. 2 squared plus 2 times 3 times x plus 3x to the second power, which is equal to 4 plus 12x plus 9 times x squared. All right, and for another example, we have 3 minus 4x to the power of 2. So 3 minus 4x to the power of 2. Now what does that look like? Well, that looks like a minus b to the squared power, where a, in this case, is equal to 3, and b is equal to 4x. Okay? And so what is a minus b to the second power looks like? Well, it's a minus b, so what we're going to get is a squared minus 2ab minus b squared. Okay? And am I correct about that? My memory, how's my memory doing? Alright, my memory is failing. It is actually plus b squared at the end. Okay. Looks like I need to work on my memory. I'm going to write some flashcards for later. I'm going to do that right now. Do I have flashcards? I got some flashcards for my machine drawing. I think I have some blank ones in here. Okay. No blank ones in here. They're supposed to be. Let's see if it has some blank ones. Alright, I won't waste any more time unless I find them right away and I don't see them. I actually, if you could believe it, I don't own a single chunk paper cutter at all. The best thing I have to cut paper is X-Acto blades and scissors. That's it. So I'm lacking in that department. But I don't want to spend the $30, $40 on a paper cutter at this moment. But I would like to be able to make these sort of flashcards super quickly without having all these rough edges of scissor cutting. Okay, so to want is to want. It is what it is. Okay, so, well, we have a squared minus 2ab plus b squared plus b squared. Okay. So all we have to do is plug in 3 and 4x wherever we see an a and a b, respectively. So 3 squared minus 2 times 3 times 4x plus 4x in parentheses squared. And then we just follow this through. 9 minus 2 times 3 is 6. 6 times 4 equals 24. 4x plus 16x squared. Okay. So then we have our answer here, just as we had. So 9 minus 24x plus 16 times x squared. Now, I don't like it in this form. I like in order of powers. I like it like this. Okay. So then we have another example here. Okay. We have minus 2a plus 5b in parentheses raised to the second power. Okay. Let's write that out. 2a plus 5b to the second power. So what does this look like? Well, this looks like a plus b squared. Okay. Where a is equal to negative 2a and b is equal to 5b. Now, using this with a and b over here is a bad idea because this relates the same ones. So instead, what I should have done is replace a and b over here with another value, say x and y. Okay? So what is x plus y to the second power equal to? Well, that's quite simple. That is x squared plus 2xy plus y squared. Okay? And all we have to do is plug in minus 2a for x's and 5b for y's. So we have minus 2a to the second power plus 2 times minus 2a times 5b plus 5b to the second power. See, like I'm like falling off the book right here. You can see I'm like right on the edge. Really hard to write. This recording thing is a skill to be learned, to be sure. Also, my beard is falling off. Keep getting hairs in the frame. Then again, I got quite a lot of hair. It's like, it's okay if it's attached to you. But as soon as it falls off, it's blah. It's gross. But it's me. And then it's not me and it's gross. Okay. So let's just follow through on this. So we have minus 2 times minus 2 and a squared plus, let's bring all of these here. So we have 2 times minus 2 times 5 times ab plus 25b squared. And so here we have minus 2 times minus 2. That will equal positive 4 a squared. And then we have plus, well, we have a minus in here and everything else is positive, so this is no longer going to be plus. Guaranteed. It's going to be minus 2 times 2 equals 4 times 5 equals 20, so that'll be 20 AB, and this is going to be plus 25 B squared, and I'm going to write it the way I like it in order of powers, highest to lowest, 25 B squared. Well, actually, there isn't any orders of powers. This one did, with only one ordering. This one did not, because of separate ones. I could have the squares over here, but I'll leave it as is. I mean, the book did the same here, so it looks like we got the same result as over there without looking. Alright, and we have one more final example. We have 4a minus 6 times 4a plus 6. And this will equal what? Well, this looks like a minus b times a plus b. Okay? Because we can see that 4a equals 4a and 6 equals 6, but we have the plus and the minus difference. Okay, and we know, what does this equal? Well, we know that a minus b in parentheses times a plus b in parentheses equals a squared minus b squared. Okay? So, and this will be where a equals 4a and b equals. See, I just don't like it with the a's and the b's, because that a is not the same as this a. Don't like it. I don't like it. We shall live with it. And b equals 6. Okay, so all we have to do is plug in for 4a where a is and 6 where b is. So we have equal to 4a to the second power minus, that was poorly written. Second power minus 6 squared. So that will equal 16a squared minus 36. Because 6 times 6 equals 36. Okay, well, there's that. And is that what we got in the book too? That's what we got in the book too. So we can take this away, so we need it again, and continue on. We have discussed so far examples of products of two factors. Of course, we can take products of more factors using associativity. So, for example, expand the expression to x plus 1 in parentheses times x minus 2 in parentheses times x plus 5 in parentheses as a sum of powers of x multiplied by integers. That's actually a writing, it's not a hair. Okay. We first multiply the first two factors and obtain. So we're just going to take 2 times x plus 1 in parentheses times x minus 2 in parentheses. So we're just going to do these two first. Bring them up here, work them as a separate problem, in which case we will, well, we're following the distributive property of 2x plus 1 into x minus 2 because, and we can't use our previous convenient functions that we can memorize because a does not equal a in this circumstance. 2x does not equal x. That fails the first test. So we can't use any of them. So we just have to use bare brute force instead of convenient memorization. So we have 2 of x times x minus 2, and then we're going to have 1 times x minus 2. Okay, then distributing in 2 sub x, well, 2 times x minus 2 is going to equal 2x squared minus 4x. With 2 times 2 equals 4, with x, 4x. Plus 1 times x minus 2, well, it's just 1, so it's not going to change anything, so it's just plus x minus 2. We have equal to 2x squared minus 3x minus 2. We now multiply this last expression with x plus 5 and obtain 2 times x plus 1. What? Oh, okay. So it's showing the original question over here. So it says repeating the original question and then substituting in our answer from above. Confused me for a second. So we have the original question, 2 times x plus 1 in parentheses times x minus 2 in parentheses times x plus 5 in parentheses. And we can substitute 2 times x plus 1 in parentheses times x minus 2 in parentheses to be 2 times x squared minus 3x minus 2 in parentheses. And, of course, with our unchanged x plus 5 in parentheses. So then, what we could do is we could distribute. So the distributive property works in both ways. So we can come from the left and we can come from the right. In this case, we're coming from the right because it has less factors. I'm not quite sure what to call them. Well, we have less things. We have 1, 2, 3 on the left, and we have 2 on the right. So let's go 2 into 3 because it's more convenient to write. So we have 2 times x squared minus 3x minus 2 times x, and then we have the same thing times 5 on the right. So we distribute x into our 2 times x squared minus 3x minus 2 to equal 2 to the x cubed minus 3x squared minus 2x. So we're raising each one of these up by x. Well, we're not raising up any of them. Well, we're just simply multiplying them in. But we're raising these powers. So x squared becomes x cubed, x becomes x squared, and x to the 0 or 1, it becomes x. So x becomes from x of 0 to x of 1, which is just x. And then with 5 distributing in, so 5 times 2x squared minus 3x minus 2 in parentheses will equal our 2 times 5 is 10x squared minus 3 times 5, 15x minus 2 times 5, 10. Which leaves us with 2x cubed minus 3x squared minus 2x plus 10x squared minus 15x minus 10. So if we have our grouping all of our to the third power of x, we just have 2 to the third power of x. Well, x to the third power, so then we're just going to drop that down. But then we have several x squareds, so we have minus 3 times x squared, and we also have plus 10x squared. Okay, so what we can do is we can add those together to get 7x squared. And then we can do similar with minus 2x and minus 15x. We can add those together because they have the product of x. So we have minus 17x. And then lo and behold, we have our only constants, minus 10. So we have minus 10 at the end, which is the desired answer. Okay, that completes the rules for multiplication, section 3 of chapter 1 on numbers of chapter 1 on numbers of basic mathematics by Serge Lang. Next video, we will be concluding with the exercises that we just reached and a little typo in the book that we'll go over. Thank you for watching.